So this is the Laplace transform of 1 by epsilon w t minus epsilon. And there is 1 minus epsilon s by 2 factorial plus epsilon s square by 3 factorial and so on. And we know that delta function is the limit when this tends to 0. Therefore, the Laplace transform of delta function, this is equal to limit epsilon tends to 0, the Laplace transform of 1 by epsilon w t comma epsilon. When this is limit epsilon tends to 0, 1 minus epsilon s by 2 factorial. From this, we are simply substituting this expression here, plus epsilon s whole square by 3 factorial and so on. So all other terms will contain higher powers of epsilon s. So when epsilon tends to 0, this becomes 0, this becomes 0, and all higher powers of epsilon will become 0. What remains is only 1. So this is equal to 1. Okay, so this is fine. That means the Laplace transform of delta t, this is nothing but 1. Okay, this is fine. Then let us consider some conditions. So far we have looked at 8 different examples of how the Laplace transforms are calculated. Then if I give you an arbitrary function, and ask you to calculate the Laplace transform of that function, will you be able to find the Laplace transform of that function? I mean, for any given arbitrary function, does the Laplace transform exist? Or is there any condition for the existence of Laplace transform? That is what we are going to see now. So let me take a sheet of paper. What are the conditions? What are the conditions for the existence of Laplace transforms? So let me write it here. Conditions. Conditions for existence of Laplace transform. Conditions for existence of Laplace transforms. Condition number 1, the function ft must be of exponential order. And what does it mean? It means that is f of t, the modulus of this function, should be less than some number m e to the power alpha t for all t greater than or equal to capital T, where m alpha capital T are some positive quantities. That means for the Laplace transform of this function to exist, this Laplace this function should be of exponential order. Okay, and what is the meaning of the function being of exponential order? It means that I should be able to find some positive numbers m, alpha, and t such that the magnitude of the function is less than m e to the power alpha t for all values of t greater than capital T. This is the meaning of a function being of exponential order. So the first condition is that the function should be of exponential order. And this is to ensure that the Laplace transform integral that the Laplace transform integral is finite. Okay, so this condition that the function f of t must be of exponential order, this condition ensures that the Laplace transform integral is finite. Okay, that means the function does not grow too fast. This is the growth restriction condition, also called the growth of exponential order. One example is that we have already seen that the function e to the power t square does not satisfy the above condition. Does not satisfy the above condition. That means the function e to the power t square is not of exponential order. Okay. Then the second condition. Let us come to the second condition. Condition number 2. The second condition is piecewise continuity. Piecewise continuity. Piecewise continuity. Okay. The second condition is that the function ft should be piecewise continuous. Okay. Before I continue further, let us first explain the meaning of piecewise continuous function. Okay. So a function f of t is said to be piecewise continuous. Piecewise continuous in an interval if two conditions are satisfied. Number one, there are a finite number of discontinuities. There are a finite number of discontinuities. Let me make some space for the graph here. Okay, this is t, this is ft. Number 2, the limits of f the limits of this function f of t as t approaches the endpoints of each subinterval. Subintervals are finite. Okay, so when is a function said to be piecewise continuous? A function is said to be piecewise continuous in an interval if inside that interval there are only a finite number of discontinuities of the function. Number 2, the limits of the function as t approaches the endpoints of each subinterval are finite. So let us consider a function. Let me draw some intervals first. The function is said to be piecewise continuous if the function is something like this. In this subinterval, it is like this. In the next subinterval, it may be like this. Okay. And then in the next subinterval, it may be like this. Then in the next subinterval, it can become like this. Okay. So at this point, the value of the function suddenly jumps from this point to this point. So this is a point of discontinuity of the function. Similarly, at this point, the value of the function jumps from this point to this point. So this is another discontinuity of the function. Then again, at this point, the value of the function suddenly jumps from this point to this point. So this is another discontinuity of the function. Okay, so this function can be divided into a number of subintervals, and inside each subinterval, the function is continuous. Okay, so inside this small subinterval, the function is continuous. Inside this subinterval, the function is continuous, but overall, the function is discontinuous. Okay, Shidari continuous OI, here also the function is continuous. Here also the function is continuous, but overall, there are many points of discontinuities. So this is about condition number one. There are a finite number of discontinuities. Number two, at the endpoints of its subinterval, the value of this function should be finite. So this is a finite number, 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 this is a finite number. So at the endpoints, the value of the functions are also finite. That means this function is piecewise continuous. Okay. If you want to see some function which is not piecewise continuous, then you take the example of tan theta. Tan theta. Let me show you the graph for tan theta. Let me stop sharing the video. Okay. It's taking a long time to open the web browser. I'm opening the web browser and I'm going to show how tan theta looks like. The graph of tan x. Today the system is a little slow. Graph of tan x. Okay. Let us look at the graph of tan x. So this is the graph of tan x. Fine. At x equal to pi by 2, there is a discontinuity. At x equal to pi by 2, there is a discontinuity, but this is not piecewise continuous because at x equal to pi by 2, the value of the function goes to infinity. This is not a finite number. Okay. For the function to be piecewise continuous, at the endpoint of each subinterval, the value of the function should be a finite quantity. But here, at the end of this subinterval, the value of the function goes to infinity. Okay. So the second condition is not satisfied. The second condition is not satisfied. That means this function. That means this function, graph of tan x, is not a piecewise continuous function. Okay. So let me come back to my camera. Okay, this is fine. So this is an example of a piecewise continuous function, but tan x is not piecewise continuous. Okay, so now let us write down one theorem. Let me write on new sheet of paper. So let us write down one theorem. So theorem one. Theorem one. And what does it say? If the function f of t is piecewise continuous, in every finite interval, in every finite interval, 0 t less than equal to t, where capital T is some finite number and is of exponential order for small t greater than capital T. Then Laplace transform of the function f of t exists for the values of s greater than alpha. So we mentioned two conditions here. The first condition was the wave function must be of exponential order given by this expression, and the second condition is the condition of piecewise continuity. So using these two conditions, we have a theorem which says that if the function is piecewise continuous in every finite interval and is of exponential order, then the Laplace transform of the function exists. The next point is, are these conditions required for a function to have a Laplace transform, or these conditions are not at all required? Meaning, are these conditions really necessary for a function to have a Laplace transform? The answer is that these conditions are only sufficient and not necessary. Okay, so what does it mean? It means that if a function satisfies these two conditions, then the Laplace transform of the function will exist. So this is a sufficient condition. So if these two conditions are satisfied, then the conditions are sufficient that the Laplace transform exists. But these conditions are not really necessary. That means there may exist some functions which do not satisfy these conditions, but still the Laplace transform of the function exists. In other words, Laplace transform of f of t may still exist even though the conditions are not satisfied. Even though the conditions are not satisfied, the Laplace transform may still exist. Example, we just saw that the Laplace transform of t to the power n, this was gamma n plus 1 divided by s to the power n plus 1 for n greater than -1 and s greater than 0. Okay, now if I take n equal to -half, okay, if n equal to -half, and -half we know is greater than -1, so this condition is still satisfied. We have, I repeat, if n equal to -half and -half is greater than -1, so this condition is still satisfied. We have Laplace transform of t to the power -half. This is equal to gamma of -half plus 1. So this is gamma half divided by s to the power half. So this is nothing but root over pi by s. Okay, root for both pi and for s. So when n is equal to -half, the Laplace transform of the function exists. But this function f of t is equal to t to the power -half is not piecewise continuous. Is not piecewise continuous on the interval on the interval 0 less than equal to t less than equal to capital T. That is t lying between 0 and capital T, where capital T is any positive number. Because when t goes to 0, when small t goes to 0, this is 1 by square root of 0. And 1 by square root of 0 is infinity. So this function is not piecewise continuous, because at the origin, this function goes to infinity. So even though this function is not piecewise continuous, its Laplace transform exists, and it is equal to root over pi by s. So this is one example of a function which does not satisfy the conditions for piecewise continuity, but still the Laplace transform exists. Okay, this is fine. Then let us write down one more theorem, and then we'll wind up. So theorem 2. So let me write it on a new sheet of paper. Theorem 2. Theorem 2 says that if f of t satisfies the conditions of theorem 1, then, so what are the conditions of theorem 1? There is piecewise continuous and exponential order. Then limit s tends to infinity, Laplace transform of f of t. This is equal to limit s tends to infinity, f of s. What is f of s? F of s is the Laplace transform of f of t. So Laplace transform of f of t is written as small f of s, and this would be equal to 0. So if the function satisfies the condition of theorem 1, then when s tends to the limit s tends to infinity, Laplace transform of ft should be equal to 0. It follows that if limit s tends to infinity, f of s is not equal to 0, then ft cannot satisfy the conditions of theorem 1. Okay. So I repeat, if the function f of t satisfies the conditions of theorem 1, then the limit of the Laplace transform of that function, the limit s tends to infinity, should be 0. And if this is not 0, then the function cannot satisfy the conditions of theorem 1. Then finally, we'll write down one property, and that is the uniqueness property. Uniqueness. And what does it say? If the Laplace transform of a given function exists, then it is uniquely determined. I repeat, if the Laplace transform of a given function exists, then it is uniquely determined. It means that transform is unique. I repeat, if the Laplace transform of a given function, if it exists, then that transform is unique. Okay. But the same is not true for inverse Laplace transform. Okay. So I repeat, if the Laplace transform of a given function exists, then the transform is unique. But the same is not true for inverse Laplace transform. Example, this would be the last example for today. Example, if f of t is defined like this, this is equal to t when t is not equal to 2, and this is equal to 10 when t is equal to 2. Then we can show that Laplace transform of f of t, this is 1 by s square. We can show that the Laplace transform of this is 1 by s square. Okay, but f of t is not equal to t at t equal to 2. 1 by s square, we also know that 1 by s square is the Laplace transform of t from this formula. From this formula, if we take n equal to 1, if you take n equal to 1, then this becomes gamma n 1 plus 1, that is 2 divided by s square. And what is gamma 2? Gamma 2 is 1. So Laplace transform of t is 1 by s square. Okay, I repeat, Laplace transform of t is 1 by s square from this formula. And we also find that for this function, the Laplace transform is also 1 by s square. So now we have two functions whose Laplace transform is 1 by s square, and these two functions, one is f of t, the other is t, and these two functions are not equal at the value t equal to 2. Although ft and t have the same Laplace transform. Okay. Here it means that this function f of t and t, they have the same transform 1 by s square, but they are not the same. Okay, so so we have found two functions. One is f of t and the other is t. They have the same Laplace transform, but the two functions are not equal. So that means the inverse Laplace transform of 1 by s square, this is not unique. Okay, so what is the general idea? The general idea is that if two functions differ at finitely many points, if two functions differ at finitely many points, then Laplace transform of these functions, Laplace transforms of these functions are the same. So finally, I repeat, if two functions, they differ at finitely many points, then the Laplace transforms of these functions are the same. So we see that the inverse Laplace transform is not unique, but the Laplace transform is unique. So that is all for today. Let me stop the recording.